Come in, X-ray Mike Victor, X-ray Mike Victor. We're tracking you at a height of 3,500 feet, 120 knots on bearing 120. Please confirm, X-ray Mike Victor. Ah, what's all that? Well, I think it was the control tower talking to X-ray Mike Victor here, this little dude. And what they were doing was describing the position of the plane. Okay, where it was, what direction it was heading in. Hey, that's our introduction to vectors, where in that case we had a specification of a height, a direction, and a speed. Okay, so that was a three-dimensional sort of description of the position, and that's our introduction to vectors. Vectors are a way of specifying the magnitude and direction of some quantity. Okay, magnitude and direction. So it's quite often used in plotting paths of planes and boats and so on. And here's a cockpit of that little plane up there. Uh-oh. No, I don't think so. Looks like it comes from a bigger one. I don't think that would ever fit in that little plane, would it? The whole thing's bigger than the plane. Anyway, so here these dudes are plotting their flight vectors and so on, their height, their speed and so on. So what we're going to do is start off not with the three-dimensional case, but just two-dimensional flat cases. Then later on in the second part of vectors presentations, we'll look at 3D problems. What about this thing over here now? I think you can start to see there is a way we could represent these quantities. We want to specify some direction. Here, this one's 45 degrees from true north, and this is its magnitude, 50 newtons. This might be a force of a wind on a boat, for example. So we want to specify the direction and the size. So what about using lines? They would have to have arrows on the end, wouldn't they, to indicate the direction. And we could, use a scale for the length to represent the size of the quantity. Come over here, these two. What do you reckon? They're parallel, so therefore in the same direction, and they seem to have the same length. So we might say this vector is equal to this one. Look at the arrows now. We're going to use that to distinguish the fact that B is not the length of a side, it's a vector. Okay, it's representing a quantity which has a certain direction and magnitude. So that's our notation, building up quite quickly, this desire to indicate the size and the direction of some quantity. What about these two over here? What do you reckon? What would you say about their direction? Well, it's the same orientation in space, isn't it? Same direction, but B is shorter than A. So we'd say A is not equal to vector B here. And what about these two? They look to have the same length, same size, but they're off at a different angle, aren't they? So again, these two vectors are actually not equal. So for vectors to be equal, they have to match in the direction and also the magnitude. Are you getting the idea here of a vector? All right, well, let's go and have a look at the origin of vectors from a geometric point of view and then come back and look at their usefulness. So I want you to think about vectors in terms of geometry, and here's the Cartesian plane again, and this really has got an arrow there, but you can't quite see it. I want you to think of this vector as a displacement of point A to point B. So a vector in geometry land now, I want you to think of as a displacement of points on the plane, displacement of points on the Cartesian plane. Okay. We have other ways, other forms of geometry, don't we, where we think of lines as y equals mx plus c, coordinate geometry, and distance between points. And then in deductive geometry, using Euclid's theorems, Euclidean ideas, to talk about lines and parallel and so on. So I'm going to ask you to think about geometry up here in vector ideas, vector geometry, where we think of creating a line by displacement of points on the plane. So this line AB going from A to B represents the displacement of the point A starting here and moving it to B. Well, how would you describe that? Can we analyse it? Well, it consists of two parts, doesn't it? Really, we're moving it in the x direction across here by that amount. So that's our first part of our displacement, and from 1 to 5, so it's a matter of 4 units there. And then we're moving it up to there. So we're moving it vertically. Now how far? We've got different scales here. So this is 16 over here, and down here it was 4. So that's a distance of 12 units. So yeah, we could describe that vector AB. Why is it a vector? Well, it has a magnitude for the displacement, how far A has been moved, along here, and a direction, okay, to describe that line AB. Now, we're not going to use slopes. That's coordinate geometry. We're going to use something else. Have a look and see if you can see what I'm doing here. I'm going to say the vector AB is represented by that. Can you see what I've done? I've said it's A has been moved to B by a component of 4 units in the x direction and 12 in the y direction. What a neat way of representing the magnitude and the direction of that displacement or that vector. We're going to use these arrows here to indicate the direction, A to B, and then the notation here which will accommodate all that we need to show in the direction and the magnitude of the vector. My burning question I'm going to leave with you is, how long is vector AB? Okay, you might know a little bit about this from before. I'll give you a hint. There's a right angle there. Okay, have you worked it out yet? Alright, I'm going to leave you with that because I want to develop this idea of a different form of geometry as a way of looking at vectors. Does this ring a bell? I think it's something to do with the midpoint theorem of in triangles, where it says, what does it say? Do you remember? The line joining the two midpoints, and we've got midpoints here, of any two sides of a triangle is parallel to the third side and half its length. So we want to prove that now. Let's see if we can prove that DE is parallel to AC and DE, length of DE is half the length of AC. Now we'd normally do this in coordinate geometry land, wouldn't we? We'd assign coordinates to A, B, C, and then work out, and D and E because they'd be the midpoints, and then work out slopes and lengths. It's quite a long process. Do you want to see a neat way of doing it with vectors? Let's just scrub these things out here and see if we can do it nice and neatly with vectors. All right, let's say line AD. Let's think of that as the displacement of A to D. Let's call that vector A. Okay, and then let's think of BE, displacing B to E, as the vector B. Now, what can you say about line AC, the base, because we want to do that over here in the proof. So let's have a look. What can we say about the base AC? Well, remember we're in vector land, so we're going to think of that, the displacement of A to C is our line AC. What have we done? Well, let's go right round the outside. First of all, let's displace A to B. Well, that would be this vector. Oh, hang on. Can you see that DB is in the same direction, the same straight line, and because it's a midpoint, this is vector A as well. So to go from A to B, we're going 2 lots of vector A. Let's come down here. What about E to C? That's on the same line as B, so it's got the same direction. Because this is a midpoint, that's B as well. So what could we say? AC, the overall displacement of A to C, could have been thought of as going the long way around, 2A plus 2B. Couldn't it? That's a nice, neat way of describing AC. That's a description of the displacement of A to C in vector land. Alright, well, what's the other one we want to compare it with? DE. Let's try and look at the displacement of D to E. Here it is here, going this way. D to E. What is it? Well, you could go around the outside as well. You could say it's equivalent to displacing D to B and then B to E, which would be A plus B. Can you see we've just done it? Because AC is 2 lots of, we'll come and talk about this later, whether you can do this, 2 lots of A plus B. In other words, that vector AC is twice vector DE. Now, it's got the same direction, it's just double its size. I think we've done it. That's what we wanted to prove. So we would say, therefore, DE is parallel to AC, and the size of DE equals, I will put it slightly differently for what we've put here. We've got the size of AC equals twice the size of DE. And that's what was required. So we'll put as required down the bottom here. Alright, quite a neat way, isn't it? No big formulas and stuff going on as in coordinate geometry. So I wonder, with you thinking about the midpoint theorem and how we can use vectors here, it's a 3-line proof basically to achieve that result. So some thinking there. That's what I want you to think of now. Thinking of geometry as displacement of points on the plane, not as mx plus c, not as Euclid's theorems, but a different way of thinking. And this is very powerful in applying vectors later on. Okay, let's go on and have a look at expanding that notion a bit. Well, here we are. What would you say about vector u and v? Now I want to pause here, because see how that's in bold, u and v? We on paper will have to write this, because it's very hard to write u in bold. See, it gets to be a mess. So we're going to use the arrow notation versus books that use the bold letters. Okay, when you see bold letters in any text, you know that represents a vector, like it does here. Well, I think you've got the idea. P has been displaced from the origin to Q. So that's a vector, and how could we specify it? Can you work it out in a column matrix or column vector way? It's been moved across to and then up, how far? 5. So it's a vector 2, 5. Oh, that's the same as the coordinates of the point. How does that work? Well, when you're coming from the origin, of course, it will always be the same. And this is called the position vector. Position vector. Or I think we'll be taking some screen clippings from Pearson's, and they call it the standard vector, or vector in standard position coming from the origin. So then the components are exactly the same as the coordinates. Now please note that Pearson's also use the notation 2, 5. Now in the syllabus, the IB states this vertical way of doing it, a vertical vector there, a column vector, not this way. And I think you can see one of the reasons this way could confuse you with an actual point rather than a displacement. Okay, what about this one over here? Gee, V looks very similar, doesn't it? Looks parallel. Let's check it out. going across 2, and then up here, yeah, I think it's the same, 2 and then 5, yep, from 1 to 6. So, yeah, they are both a vector 2, 5, starting at different points. One's a position vector, thinking about displacing the origin to 2, 5, and the other vector, starting at a different point. They're still equal, though, because they're equal in magnitude and direction. It's displacing the point 3, 1 to 5, 6. So we would say these vectors are equal. Please note they don't start at the same point with their displacements. But vectors are quantities which have magnitude and direction or represent the same displacement of points on the plane. So you're going to go the same amount, but maybe starting in different spots there. We'll have a look at that again later on. Now, you're getting the hang of this. It's a new way of thinking, if you like, a new system that's quite useful. Well, here's a puzzle for you. I've got a puzzle here. I want you to consider, here you are, you. There you are. And you're going to walk along this park. You're going to go to there, go to there, go to there, and back again. And what we'll say is I'm going to call this vector u, where you start off there, and this vector v, and this vector r, and this vector s. I don't think I actually have to use different letters for all these. They're quite related, but we'll look at that in a minute. So I want you to tell me, overall, when you move u, displace yourself to here, then go to v, then go there and back again. Could you write an expression with u, v, r and s that describes your motion? What have you done? Okay, let's do it. You went to there, then you added the displacement of v and got to here, then you added the displacement of r and got to here, then you added the displacement of s, and what did you end up with? You went nowhere. Oh, the idea of a zero vector, but we should have the arrow there for that one, not just zero, it's not a number. It's a sum of displacements. It's a sum of vectors, isn't it? Sum of displacements. As you displace yourself around that figure, sum of displacements. That's a powerful idea as we build it up here. So you can add displacements one after the other. That would seem reasonable. All right, let's go down and build a bit more here now. Here's a bit of theory for you. In general, if you're taking any point in the plane and displacing it to some other point, which has been doing this, what will you do? Well, you'll take away their x's to find how far you went in the x direction, and take away their y's here. So this should be, over here, y2, take y1. See how far in the y direction you went. So they will be what we call the components. So vector u, they've got bold. Can you see the error? Or is it an error? Let's have a look up here. Oh, I think it is. Oh, well, not necessarily. We're talking, well, they put u, which is a vector, so, it should have an arrow, shouldn't it? Right? Vectors have a magnitude and a direction. So we should be explaining which direction u is in. Right, they put a bold letter there, so therefore it means it's a vector, and we can specify it like this, u1, u2. That's a column vector. Okay, and again Pearson's will use this for vectors. Bit of confusion with the point notation there though. So the syllabus statement says they want you to use a column vector there to distinguish it from a point. So it's a movement anywhere on the plane, an amount in the x direction of u1, an amount in the y direction of u2. So that's just a formal statement of what we were doing before. So don't get too worried about that. You don't have to actually do any proofs like this in this particular course. All right, getting the idea of this description of displacement. So here's Pearson. screen clippings here from Pearson's textbook, so you should have that handy by maybe. So find the components and length of the vector between the points neg 2, 3 and 4, 7. So how far has it gone in the x direction? Neg 2 to 4. So it's 4 take neg 2. That's the x component. How far has it gone in the y? 3 to 7. So it's 7 take 3. Very similar to finding the slope y step and x step, isn't it, in coordinate geometry land? So the vector is 6, 4, and it should be written this way. That's the syllabus statement. What about the length? Uh-oh. This is the answer to the question I asked you. Let's have a look at why the length is that. We're going from neg 2, 3, so here we are. Neg 2, 3 is that point. Neg 2, 3 up to 4, 7. 4, 7 is up here. 4, 7. Okay. And we're going from there to there. Displacement of P to Q. Uh-oh, can you see it? It's what I put in before. Did you think about it then? It's Pythagoras, isn't it? So this is a distance of 6 units in a positive direction here, going along from P to Q, and 4 units up here. So by Pythagoras, the length of the vector, L squared, square on the hypotenuse, sum of the squares on the other two sides, by Pythagoras. So L squared is 16 plus 36 is root 52, and you could break that down to perfect square, the root of 4 by 13, which is root 4 by root 13, or 2 root 13, if they asked it in simplest third form. Otherwise we could just leave it like that. Okay, so it is Pythagoras again, isn't it? Same notion, how important that is there. Could you draw another vector 6, 4? Well, I could start one up here. I'm going to start one there. 6, 4, 3, 4, 5, 6, 4, 1, 2, 3, 4. There's another little dude there. Vector 6, 4. So just notice there, what I refer to as the non-uniqueness of this specification. It's unique in the sense that it specifies magnitude and direction very nicely, but it doesn't say where does it start. Okay, so 6 4s could be anywhere on that plane. Okay, can you see the power of this little notation in being able to describe those quantities? So let's draw some here. I want to draw the position vector 6, 4. Position vector, or vector in standard position means start at the origin. Go 6 and then 4. So there's my position vector, 6, 4. But hang on, there's one over here as well. Let's start here and go 6, 4. 6, 4. There's another one. Another vector 6, 4. Non-uniqueness of that notation in the sense that it specifies direction and magnitude very nicely. It doesn't tell me where to start. I'm going to draw one down here now. I'm getting excited with this. 6, 4. So there's another one. Okay, what about one up here? 6, 4. Clearly, they are all parallel and they all have the same length. So you don't know, you need to specify the starting position of that vector. Okay, because otherwise it could be any of the dudes I've actually got on the screen there. The only one that has got a special name here is this one from the origin, 0, 0. It's called the position vector of the point. And what do you notice? The components or parts of the vector, the movement in the x, movement in the y, is the same as the coordinates of the point, isn't it? Because you're starting at the origin. Okay. Whereas in these other points you're starting at a particular point. This one is starting at 13, 4 and going to 19, 8. Okay. So that's harder to see the 6, 4 nature when you're going between points like that. But starting at the origin, go 6, 4, you'll be at the point 6, 4, and that will match the components of your vector. And we remember now do a a column statement there, vertical statement there, to distinguish it from, this is the actual vector movement, this is representing this, whereas that's representing just the point. Okay, subtleties there, some little subtleties. Okay, let's get going now. Are you getting the idea? Well, what can we do with them? Well, how can we operate with vectors then? Well, I think you've seen some ideas. If you've got u going off in that direction, you want to half u, you're going to halve its length, but keep its direction. So it's going to be parallel. And 2u, it'll be twice as long, but still parallel. Uh-oh, what's this? What have they done here? Oh, bringing in negatives. Let's have a look at that. A negative in mathematics means what? Well, on the number line, it means opposite direction. So let's keep that idea in vector land and say, well, if this is u, neg u is simply opposite direction. Okay, so keep that idea. It's all nice and consistent. Maths is pretty consistent. Not too much ambiguity in mathematics, mate. And what about neg 3 over 2u? Well, it's got to go in the opposite direction to u, and it's going to be 1.5 times as long. So this one should be 1.5 times this one. Nice little symbols here, isn't it? Very concise and neat way of representing magnitude and direction and comparing things, boat speeds and so on. Very neat. Okay, getting the idea. We'll come and do some problems in a minute. Okay, so from just what I said there, this is from Pearson's now, it becomes clear from this discussion that for two vectors to be parallel, it is necessary and sufficient that one is a multiple of the other. So if something's just a number out the front times the other one, and we're going to use the word scalar. In other words, just a number, not a vector, just a number. So we're going to use numbers in vector land. We're going to call them scalars to indicate just a number, no direction. It's not a directed quantity. Okay, so we use letters like this with no bold. V and U will have directions, and we're going to write them like that. K is not in bold, it's simply a number. It's how many multiples, how many lots of that displacement. So what would we say here? Again, this is a vector, so we should put U1, U2. Then V equals KU means it is K lots of that vector, which means you've gone k times as far in the x and k times as far in the y. Okay, so in other words, you have k times u implies you have displaced the point. I'm getting back to that idea, displace the point k times as far in the same direction. Okay, that's what it's saying. So it's k lots of the x and k lots of the y displacement. You can see why. To maintain the direction, you have to do the same to both x and y components. So this is our definition of parallelism now. If one vector is a scalar multiple of the other, they will be parallel, and it will be k times as long as the other one. Okay, building, displacement of points in the plane. Please hold on to that idea. Alright, so I'm going to put vector, I'm going to make this a vector now. Remember, vector has magnitude and direction, so you must specify the directions here. So I've just drawn the vector AB and EF. AB is the displacement of point A to point B in the plane. Vector E to F is the displacement of E out to F there. Okay, what do we want to do? Well, the question here is, can we add those displacements? Is there such a thing as AB plus EF? We're doing operations with vectors now. Can you actually do that? What would that mean? Think about displacements and see if you agree with this diagram. Okay, what have I done? I've put AB and then after that I put BF. I think they say head to tail or something like that in physics. Don't like that much myself, but it works. Because AB plus EF would mean what? AB plus EF would mean displace A to B and follow by a displacement equivalent of E to F. Well, we'll stick it on the end. That doesn't. That was from E to F, but an equal vector would be started at B and displace B to F like you did E to F. But you've got to follow it by, followed by an E to F type displacement. It's not E anymore, but we've said already vectors are equal around the plane even if they don't start at the same point. So what's overall happened? AB plus EF has landed A out at F. Hey, that makes sense. That's consistent. It's the sum of two displacements. So it will have the overall components of displacement of that's the X. And what do you notice? That's going to be the sum of that X and this X. So you're going to sum the X displacements and also sum the Y displacements to get that overall displacement of point A after two displacements have been added. Getting the idea? It looks pretty powerful, this stuff is coming up now. Okay, so let's go down and build on that. Here we are. Here's our definition. If you're going to add two vectors, start anywhere on the plane. There's our first displacement. Then at the end of that, you're going to displace it further, because that's what this says. Add up two vectors, add up two displacements. Where will the point go? It'll end up out here. So that's U plus V. Okay. All centered around you're thinking about vectors from a geometric point of view as displacements of points in the plane. Okay, that's an idea that is going to be powerful in all applications of vectors as we go on to more applied problems. Okay, so here we have it. Let U and V denote two vectors. Draw the vectors such that the terminal point of U, gee, that's complicated, that's the tail of U, and the initial point of V coincide. So that we're saying displace the point U and then add on to that displacement of the point V. Okay, so that makes a very nice triangle method of adding two vectors. Okay, and it's quite reasonable and commonsensical to see how that works. There is another way, we'll just mention this, and that's using a parallelogram method. It's less obvious as to why this works. See, here we're going to U, displace that, and here to V, and then we complete the parallelogram, and the answer is a diagonal. A little bit harder to understand. It's easy to say, well, there's a displacement from that point to there, and then we follow it by put this over here. That's equivalent to V, isn't it? So overall you get there. So that's the idea. But the diagonal of that parallelogram also represents U plus V. Less obvious connection there. Okay, what's possible now? Can you subtract vectors? Talk about adding them and multiplying and going different directions. Is it possible to have U take V? Well, I think we've got to question something first, don't we? What is subtraction anyway? What's subtraction of numbers? I don't know. Can you have 3 take 5? Yes, I think you can. Let's have a look. We start at the origin, we move out to 3. There we are, we've gone out to 3. What does 3 take 5 mean? 3 take 5 is equivalent to motion 3 adding on a motion in the opposite direction, isn't it? 3 take 5. Oops, I'm falling short here. So 3 take 5 will be down here. Will be at neg 2. Ooh, that's the idea, isn't it? The secret here, and this gives rise to saying a positive times a negative is a negative, and doing that, Okay, but what we really need to question this idea here, 3 take 5, how can it have any meaning? How do you get the rules? Then what you do is you say 3 take 5 means in addition to this vector movement of 3, you now move -5. Now you're adding those two movements, aren't you? Already you have, actually working on the number line, been doing some work with vectors. Because 3 plus -5 means displace your point from the origin plus 3, and then add on to that movement -5 in the opposite direction. Think about that. That's interesting. Okay, well, what about vectors then? What will we do? Can you do u take v? Yes, we will add on to the displacement. Remember, u is a vector, it's displacement of a point. Add on to that displacement the negative or the opposite direction of displacement described by v. Okay, that's what we're going to do, say that. Okay, can we do that diagrammatically? Let's see if we can do that. Well, here it is here. So let's start up here this time. There's u. We displace to there, and here's v. So instead of adding it, which would be adding on a displacement equal to v up here, we're going to add on its negative, so we're going to go down. That's neg v. Well, what's the overall displacement of this point? It's moved to there, and then we've moved to there. There it is. The final equivalent displacement is there. Going around the outside has effectively moved it from this starting point to this finishing point. So that would be our vector u take v. Thinking about it as what's happening here, u plus the negative of v. Not up there, that's where v normally goes. It's going to be the negative of v. So we're building up a few little skills, and we'll come to practice it in a minute. Here's a little bit here for us to just get our head around. So we've got these two vectors, and again, really speaking, should be written like this. Okay, according to the IB statement in the syllabus. Write down the components of v, which is 2 times u. Well, 2 times u, got to keep the direction the same, so it's 2 times both components, which will be the vector for -6. What is the size? Well, the same thing as before, of course. It's by Pythagoras the square root of the x component squared plus the y component squared. The same in both of them. Let's just check it here. Let's do 1, 3. 1, 3. What's the length of that vector? Let's say that's w in this case. It's not what we asked for, but anyway, the length of w, so we're going to use that absolute value notation, is 1 squared plus 3 squared by Pythagoras. So the length of the vector is always the square root of the sum of those squares. And we're going to use this notation here with the absolute value or modulus notation to mean size or length of the vector. Okay. Draw some vectors and comment on the results of C above. Okay, well, let's come down and have a look at this. What do we want? We want u. Where's u? There's u, v and w. So they're all, we've started v from the end point of 2 neg 3 there. And what are we going to say? U plus w. Well, here's u plus w here, doing it by the parallelogram method. Or you could go u plus w, this being w here, coming to that point. And you can see you can do the sum of them with the components. You don't have to just draw it with the diagram. And then v plus 2w. Where's v plus 2w? Here it is here. So we're saying, where's our v? Our v down here, and then 2w. We've got this all a bit of a mess here, I think. Are they doing 2u plus 2w here for our v plus 2w, and just checking it here, our v plus 2w has to equal 6 naught. So we haven't actually shown that very well on the diagram because it's a bit messed up in here. Our v vector would be coming from back here and then adding 2w to it. Okay, so the diagram's a bit confusing there. V take 2w is parallel to u take w and twice its length. So here we need to just look at these separately, I think. So here u take w there and v take 2w, trying to look at the fact that they are parallel. Okay, and you could actually do all this with components. You could use the components of the vectors here. Okay, so it is a bit of a messy diagram. Probably it would be better to draw them all separately rather than have it all spattered on the one diagram. Okay, but not to worry. You can fathom that out eventually, but it would be good to have them all back on the one diagram. The idea then is what? You have components or diagrams. Either of those will help us with understanding. Diagrams give you a better visual picture, obviously. Components, you can just start adding them up. The components of the two vectors you're adding and look at the result. Okay, as we said before, your total x displacement will be the sum of the x's and so for the y's as well. Okay, so let's have a look at doing some problems. Now I've split Pearson's into two parts. There's another little part coming up. The questions 1 to 7 are related to what we've just done, and the other few questions on the end then are related to something that we're going to do in a minute. So I'd like you to pause the presentation now and have a go at these, and then I'll show you the rest, and then I'll show you the solutions. Okay, let's have a look then at the other ones up to 7. I've just screen clipped this a bit. Okay, have a go drawing diagrams and so on, and let's look at the solutions now. Okay, question 1 and 2, or parts of 1 and 2. Diagrams may vary depending on where your starting points are for your vectors, obviously. Question 2, finish off that. Okay. And question 3. Oops, we'll just go up a bit. Question 3. Question 4. Question 5. And question 6. A little bit of 7. Question 7. And that's it for that little group. Alright, I hope you've got some right there. Might have to check with teacher and other people to check out how to do some of those. Let's go on now to do the last little bit of this section now. Okay, so what we're going to do is look at, still playing with the same idea, but in this 2 dimensions idea, think about a vector along the x-axis as being vector I, 1 unit long. So these are 1 unit vectors, okay, along the axes. So the one along the y-axis is going to be a 1 unit vector in the y direction. Okay, so it's just another way of really explaining how you're displacing a point in the plane. How many lots of I and j you have. It's sort of emphasizing the idea that you have an x component represented by the lots of the unit vector I, and a y component by indicating how many lots of j you've got. So let's do something with that. Well, here's our vector from before, just making that clearly an arrow there. So it's placing point A to B, starting at A. Well, coming along here, we've done this before. Let's go in Xland for a start. And we've gone from 1 to, gone past that, 1 to 5 there, and then come up here. So what would you say that displacement was? Well, if we let I be a unit vector in the x direction, so there it is there, I. How many i's have we got here? Well, there's an I, there's an I, there's an I, and there's an I. So that represents 4 lots of the vector I. And up here, we've gone up to 16 from 4. We said this was 12 before. If we come back down here, and we think about, here's J, it's a different scale, so this would be vector J, wouldn't it? 1 unit in the Y direction. We've got 12 of them, 12 little J's here. So this alternative notation says that the vector AB would consist of 4i plus 12j. It's sort of a more emphatic way of writing what the displacement of A to B is. 4 lots of 1 unit in the X and 12 lots of 1 unit in the Y. Just a different notation. Can be useful in looking at stuff later on. Okay, so that's what we're now going to do to finish this little unit off. Look at that component expression in terms of the unit vectors on the axes. In component form, using I and J, the unit vectors on the X and Y axes. Okay, so if you look at vectors now, you'll have a number of lots of I and a number of lots of J. Okay, this is in comparison to U1, U2 and V1, V2, comparing the two. Different sort of notation. What will you do? Well, when we're adding them up, we used to add the X components together and the Y components together, so we'll do that now. The total number of I units moved in the X direction will be U1 plus V1 and U2 plus V2. Just in that same way. Okay, so let's do one. Let's do an actual one. If the vector U is 2i plus 3j and V is 5i take 3j, how do you get U plus V? Let's do it. So let's start U off as somewhere here, 2 and 4. So there's 2i in the X direction because I is the unit vector, so there'll be 2 of them there. So that's going to be a motion of 2i, and 4 in the J will be going up to 6 there. So it's 4 lots of movement. So that's our vector U. And then we're going to move V on the end to add on V. So what is V? 5 in the I. So where are we? We've got to go right out here. 5 in the I. Coming along. 1, 2, 3, 4, 5. 5 in the I for vector V. And then neg 3 in the J. Well, we've got to watch the scales here. So scale is 2. Got 1, 2, 3. So here neg 3j. Just another way of doing it. So overall, vector V on the end. We'll just try and get this a little bit neater in here. Vector V on the end is coming to there. So that's V. 5i take 3j. So our overall answer, U plus G, is from the beginning to the end there. Alright, we've displaced this point to U and then down to V. This is the overall vector U plus V. And what should it be? Well, if you look at it, how far we've gone here, we've gone 2I, another 5I, so that would be 7I, and then the movement the other way, though, however, is we went 4I, but came back neg 3I, that's going to have only, 4J, and then the other one, I think I put I there, that should have been a J. We will just have one J, wouldn't we? U plus V is going to be a total of 7I, but we've gone down 3J. So a lot of diagrams there, unnecessary if you can see what's happening over here. You add up the X movements and the Y movements and call them I and J. It's the same stuff. However, we're going to use I and J rather than just the numbers in component form. We're going to use component form using the I and J unit vectors on the X and Y axes. Just an alternative. Let's have a look at the differences. Alright, we'll do the same thing here. If you're subtracting two vectors, you'll subtract their X components and their Y components. So the I vectors, the I components will be U take V, and the J components will be U take V. Let's do one again. Let's do 2I plus 4J, and then we will take them away. So let's do the same thing again. Start here. 2I will take us to here, and 4J. This was 4J again. So that's our U vector, and then we want to take away V. So what that means is on the end of this, instead of going 5I this way, we want to go the opposite. So let's just write down what neg V would be. Neg V would be neg 5I plus 3J, wouldn't it? Multiplying this by neg 1, going the opposite direction. So here on the end, neg 5, I've run out of room, that's not good. So here, I'm only up to 4, now I've got to add on neg 5. I'm going to come over here, not good. Neg 5, I'll be over here even further. And then plus 3J, going up 3 in J will take us up here. I've gone off the scale, what a mess here. So I'm up there, and that's going to be my minus V, isn't it? Because I've got to come across minus 5I and up 3J. So my overall resultant vector, should have thought about that before I put the grid there, shouldn't I? Would be what? Well, here it is here. I've displaced this point to start with, U take V, so there's my U minus V. And what are the components? Well, I went 2I and then back 5I, so we're over here at neg 3I off the scale, and look at that, so back here 3I, and then how far up have we gone? We've gone 4 and then another 3J, that's 7J. Okay, so it's neg 3I plus 7J coming out that way. So you can check it with graphs. As you can see, graphing gets a bit messy compared to just taking away the components. Okay, but it's good to have a picture of what the displacement on the plane really means, and that's where diagrams help. Right, getting an idea, let's do some and see what you think. Here is a generalisation of what we've just done. If we're going to displace point A to point B, you could think of it as going around the closed figure, couldn't you? Let's go around this way. What's that? That's negative OA. Okay, O to A is that vector there. We could go neg OA and then plus OB. So AB, the displacement of A to B, could be thought of as the sum of minus OB, minus OA, and plus OB, going around the outside there. Okay, go backwards and then go to OB. Or you could write that as OB minus OA. That's an interesting one. AB is OB minus OA. Let's check it another way. Let's go OB and then minus OA. That would be down this way. Oh yes, it would be the same, wouldn't it? Minus OA, and these two would be parallel and the same length. So this is the usual way of, if you like, adding to OB minus OA. But they should give you the same result. A vector, same length and parallel. Doesn't have to be coming from the same point, remember. Non-uniqueness of that specification as to the origin of the movement. So this is the approach we get, this is the answer we get when we use the closed figure approach. That is saying the sum, as we saw earlier, sum of displacements around a closed figure are zero. Okay, so going around a closed figure, the sum of the displacements is zero. Or you would say that it's a zero vector. If you're saying U plus V plus R form a triangle, the sum of those displacements would be the zero vector, zero displacement. When you have something like this, for example, U plus V and then R takes you back here, we would say U plus V plus R is zero. So, fairly simple idea overall, but I really want you to get this idea of displacements, and then everything makes sense. Okay, come on down and let's have a look at some of the rules that we've just worked out. Many of the laws of ordinary algebra are also valid for vector algebra, so it doesn't matter which order you add them in. I wonder if you can see why. A plus B is B plus A. It's the same as why you have a commutative rule for simple addition of numbers. These are all vectors, of course. Doesn't matter which one you put first and add the other one. No, because it's the sum of displacements. And because it's the sum of displacements, then it's the sum of ordinary x and y numbers, and those sums are commutative, aren't they? Because addition is commutative. So vector addition is commutative really because adding, ordinary addition, is commutative. Does it matter the order in which you do it? For the same reason, no. Let's have a look. A plus B plus C ends us at D there, and it wouldn't make any difference if we had starting somewhere else. It wouldn't make any difference because A is displaced, or that's displacement using A, then B, then C. The overall is going to give us that one. It doesn't matter the order in which you do it. This point ends up over there, no matter which journey you follow. You could add B and C. First of all, adding B and C would give us F. A and F still give D. Okay, A plus B gives E, and then C gives our D. So the idea here is it doesn't matter which order. A added to B gets you to E, and then adding C gets you there. B plus C gives you F, adding to A gives you D. Doesn't matter which way round you get, because it's the sum of displacements. Okay, a couple more rules and then let's finish off. It's been fairly long. What's the commutative rule for multiplication? Well, if you're multiplying by a scalar, you can multiply after it if you like. Not very relevant, that one. Here, if you've got m plus n lots of a vector, then you're multiplying that vector m times, that's a scalar, and n times, so you can just add it up, or you could say it's m lots of a and n lots of a. Also, because that is a scalar multiplication, you're multiplying both components by the same number, so it's going to be able to be distributed over the two. Distributed law number 2 here, if you add up a and b and then multiply it by m, it's the same as multiplying a by m and then adding m by b, for the same reason, and that comes back to the scalar multiplication of a vector. It's m times the x component and m times the y component, that idea. So because of that, it's going to just be a simple distribution, if you like, of m lots of that vector and m lots of that vector, and you'll be able to do it separately because of this property of scalar multiplication. Remember, this is a scalar because it has no direction, it's an ordinary number, and we just introduce it in vector land so that we're clear when we are referring to quantities with letters which are vectors and which are ordinary numbers. Alright, have a go at some problems with this I and j notation here. I don't think we can get it all on the page, nearly, so you might pause the presentation. I'll ask you to have a go and come and look at the answers in a minute. So there's up to 15, or just bring 16 onto the page there. Okay, and have a go at those, and let's now have a look at the solutions. Eight through 11, a bit of 12 coming up. Let's have a look at 12 then. 12, 13 and 14. Some basic calculation there. And the last couple, 15 and 16. So there's 15 and 16. Well, I hope you're getting the idea. An interesting representation of displacements in the plane, or of quantities which have magnitude and direction. Anyway, there's a couple more presentations as we get into some interesting problems. We're just learning the tools at the moment, so I hope you're happy with that. Might have to go back and have a look again, but for the moment, it's cheers from me.